external cavity, there's many types. We either use electro-optical material to change its reflective index, or we can also use some MEM system just to change to change its position of the end mirror. So either one will change the actual light path of the passive region. So it will be a parameter you can change to change its lasing wavelength. Since you have a beta LP, which is changeable. Beta LP will lambda over 2 pi n g p. No, who is next? NP and LP. So it either change N or either change LP. So it will become a parameter that you can change. It's not fixed. So in this case, it will be interesting for us to simplify this structure with scattering matrix, so we can describe or predict its property more easily. Alright, so in order to simplify this additional segment in the cavity, we can use the transmission, the scattering, the matrix to give the whole segment into a single reflectivity. We can call it effective effectivity. So if we watch this end mirror here, that's end mirror here. So the reflectivity we see for the light coming from the active region side will be equal to, first it is R2, the red reflection between the LA and LP. And then the second is the optical feedback inside the passive region. It is the same. It will be the T2 squared times R3 exponential 2J beta B LP plus This is the same with the work we do in the February echelon. Alright. Then in this case, if we further deduce that it turns out that the reflectivity is no more a real number. It has a complex term. Since this is a complex value, and the length of LP, the total optical length in the passive region, will change the phase of your reflectivity here. If you only have a single interface, the R will definitely be a positive number. Yeah, there is nothing we can do about that. But if you can fill something in and we can actively change NP or LP, then the lasing wavelengths will be something we can fine tune. We can do a very far tune, but we can fine tune the lasing wavelengths. So so we let the lossless interface, we can write it simply simple that REFF will be R3 plus R2 exponential 2J beta LP and since this is complex value, we can just write it down as it's a moduli and a phase term. Okay, we can simplify that. So while when the C will be maximum, the first is exponential 2J beta P LP. Wow. It will reach its anti-resonance in passive region. In the other way, if the exponential is the 2J beta BLB is -1, you will reach its minimum value. Because you need to double check that why does it look a little different from the February echelon. Because in February echelon, NP, the segment has the largest reflective index. So it has a positive R3 here and also a positive reflectivity at both sides. However, for the external cavity, the active region has the largest refractive index. So Na larger than Np, larger than usually air or some metal, its N will be pretty low. So the Np is in the between of the ambient and the active region. So you actually have a negative reflectivity here. So you will find weird why exponential 2j beta BLB equal to 1 become anti-resonant. It is not a typo. Yeah, that's because it is 1, but with a reflection in the NP, it is anti-resonance for the passive region. Okay, so you just insert beta BLP as anti or the R number of the half of pi. You will get a different high value of IEF and a low value of IEF. And so the mirror loss is 1 over LA. So we directly use the LA here, divided by R1 and the IEF. So it will be a function of wavelengths. So since the IEF is high here, for example, it is beta BLB is 0 and 0.5. So if when the reflectivity is high, then its mirror loss is low. When the reflectivity is low, the mirror loss is high. So lacing will be preferred at the discrete wavelengths. It will not be uniform. We will show more detailed figure later. So this just a calculation. You just try to do that at home. I'm gonna do that here. All right. So let's try an example of internal cavity like this. Let's assume the active region has a refractive index of 3.6, which is common for gallium arsenide crystal, and the NP is 2.5. So some material, uptone material, this number is also normal 2.5, and the active region is 500 micron. The passive region is smaller, only 100 micron. Okay, and the interface, and the activated interface is lossless. Okay, so we can just assume T2 squared plus R2 squared is equal to 1. So let's reach some value first. For R1, it is reflected between 3.6 and 1 outside. So R1 is a real value 0.565. R2 is between the 3.6 and 2.5. The reflectivity is really low, only 0.18. And the T2, you just directly do that since it's lossless. Similar for R3 here. Okay. So if we just do the put all the numbers in, plot the absolute value reflectivity as a blue one, so you will see. Since we can insert different beta, beta is according to the lambda over 2 pi, right? So it will be a function of lambda. You insert different lambda, you will get a different beta BLB. Then you will get a different reflectivity here. So the reflectivity will be some low, high, low, high, low, high. And the lowest number will be around 0.5, 0.2, probably 0.26. And the high reflectivity due to the diffraction in the passive region could be doubled, more than doubled. So those with high reflectivity give you a low mirror loss. So if we insert the mirror loss as the 1 over LA divided with 1 R1 IEFF, you will see you have a loss spectrum which is varying with its wavelengths. Then we are trying to further simplify or make it more precision if we want to meet the criterion of mode spacing as well. Yeah, because in this figure we just consider about the amplitude part, but we haven't considered what its impact in the mode spacing. Because if we only simply put the IEFF here, we will neglect the optical mode spacing introduced due to this cavity. So it is not actually precise. So what can we do? So besides we introduce something called effective reflectivity, we can also introduce another concept called effective length. So the system will be actually reflectivity with its moduli and giving an additional effective length to fit the mode spacing of this wall laser. Okay, so we now describe the whole system with two real parameters. So it's no more a complex value. It's describing this spacing region with two real parameters. It's REFF and LEFF. So if we see this is for the amplitude, this is for the phase. So for the phase, then you see it because you have the original IEFF as a phase term. So for the round trip, exponential 2J beta LA will add another first phase influence due to the complex reflectivity. So in order to get a resonance in the active region, the 2 beta LA minus alpha, the reflectivity given here, the phase of the complex reflectivity should still be 2 pi n for resonance. So then we take a total differential of this equation. So d beta times LA, since LA is fixed, so DLA is 0, so we only have d beta minus 1 of half d theta will be 2 pi, and since n will be n can only be integers, so dn is 1, and we put 2 in we divide it from both sides, so we get d beta LA minus half of the theta as pi. So d beta, the epsilon rearrangement, d beta will be pi divided by LA minus 1 over 2 divided over d beta. Beta is the wave vector for the specific wavelength, and it should be in the same form if we consider it as a real length with real as a real value length. Alright. So after comparison, the effective length should be 1 over half times minus 1 d theta over d beta, and the theta is here. It can be from this side. This tedious part. Try to repeat that by yourself. You will have a more strong understanding. And the theta is 2 beta here. So there's a beta. So theta is a function, let me define it's a function of theta. Theta is the function of beta. So you can do the phi over the beta with the chain rule. Yeah, this is calculated. It could be calculated by hand. It's actually not very difficult. Alright, so we can give a quick insight. We just that LEFF as this equation, and after some rearrangement, we can directly, so this is your homework. Let LEF divided by LP. It will be an equation like this: 1 over 1 plus R2 R3 minus R2 divided by R2 plus R3, and the R2 and R3 is here. So, and we're just trying to plot with different combination with R2 and R3, and the figure is here. We'll see what happens. So the first case, if the R3 is really high, okay. So and R3 is okay. Let's keep the same R2 first. If the R2 is the same, higher the R3 means more light reflecting from the final end. That means it has a stronger diffractional effect to the active region because more light has a feedback at the final interface. So then the effective length will be longer. If there is no any diffractional effect, we can consider there will be zero LEFF in the extreme case. For example, if the R2 is very close to 1, let's say another extreme case. If R2 is 1, that means all the light will be reflected here. The whole passive region looks like it doesn't exist, since no light will going to enter the passive region. So effectively, we can treat that with the LEFF as 0, since it doesn't have really any effect. So yeah, so as R2 goes to a low value, all of the LEFF go to 0. In the other way, if the R2 is 0, its reflectivity is really low. That means there's no reflection here. Then all the LP will be counted in the whole cavity. Yeah, things like just passing through and here, and so the LEFF will merge to LP. Yeah, but if there's a some non-zero value and neither 0 or 1 values, then you can calculate its LEFF in this equation. Then we can model the external cavity with a simpler scenario with 2 real numbers, and just since this interface doesn't exist, yeah, then you are trying to reduce the whole system with a simpler configuration. Okay, so then we can replace the LEFF into the same result we derived from the lecture in the lecture A and in the lecture A. So the spacing, the most basic should be lambda squared divided by 2 NGALA plus NGPL EFF. Is a more general form. But the delta lambda n, the most basic between the reflectivity, the highest mirror loss is lambda squared over 2 NGP LP. So you will have a loss spectrum, for example, like this. But your gain spectrum surely have a mode spacing smaller than your loss spectrum, since you can tell by its denominator. Since LA is non-zero, definitely the d lambda in mode spacing will have a smaller spacing than the mirror loss variation frequency here. Then, if there is a mode spacing like here, and originally if we just use a single facet with no variation in the loss spectrum, then this mode and this mode might lace at the same time. But since we have a variation in the loss spectrum, when the gain increase, maybe one of them, the lowest point, might be closing to its modal gain, plus modal gain minus internal loss. So while this reach the criterion of lacing, for its sine mode, its distance between lacing and the actual real gain is higher than the case with a uniform loss. So the intensity ratio between the principal signal and the sine mode will be enhanced. So you get a better signal and the low noise ratio. If this mode is the only mode you require for communication. Yeah. So it is give you the passive external cavity give you a function of the sine mode suppression, which cannot be achieved with a single interface. Alright, so let's consider some the scenario between the different lengths between the length between of the length between active region and the passive region. And it's extreme case that your LP, the passive region, is much longer than the LA. So when LP is much longer than LA, that means the LA probably not so important. In this case, you will get a loss spectrum pretty close to your gain spectrum, your gain mode, optical mode spectrum, and the low spectrum. So this is not good because the side mode might also meet another minimum value of the mirror loss. So it's still the mode suppression will not be so effective. So it's actually not a good idea. The case and another case is that these two have a similar value, so that surely the d lambda will be smaller than the delta n. So it will be convenient that besides, if we can differentiate the signal ratio between the lacing mode and the sine mode, if we can change the refractive index of your passive region, the whole spectrum might shift because you are changing its refractive index, or you are trying to change its length. Either way, the part of the active region is the same, but since you are changing the total length of your loss spectrum, it's possible to let this one shift a little bit, then let this mode meet the minimum loss of the loss spectrum. Then you can pick mode actively. For example, I can let one racing ball to be 1,500 nanometer, and the other one is 1,500.5 nanometer. It is possible to pick the arbitrary mode between a small region. It is possible if you can have a very precise control about your refract index, and either refract index or the passivity length. Okay, and okay, then the case. So what's the case one? Okay. So this is the case one. If LA is much larger than LP, it is almost difficult to pick the sine move from here because it drops too many. So this explains what's the best functionality with a passive region. That you pick a active region and passive region in a similar level. That will give you the full function of the external cavity lasers.